Welcome to Deep Engineering's YouTube channel, where we bring you real-world insights from the engineers and authors shaping modern software. Today, we are speaking with Quentin Colombet, author of LLVM Code Generation, published by backend. Now, Quentin is a veteran LLVM contributor with over 2 decades of experience in compiler backend development. He's the architect of GlobalISel, LLVM's modern instruction selection framework, and serves as code owner for LLVM's register allocators. Since joining Apple in 2012, he's contributed to backend support for x86, AR64, and Apple GPUs, and has worked across a wide range of architectures, including microcontrollers, DSPs, and ISICs. Quentin's expertise isn't just technical, though. He's also a longtime mentor to interns and new contributors in the LLVM community. His new book offers a deep dive into LLVM's backend infrastructure, guiding readers through the process of transforming LLVM IR into optimized machine code. And he's here with us today to talk about the internals of code generation, how to build and extend LLVM backends, and what it takes to contribute meaningfully to one of the most influential compiler ecosystems in the world. So a very warm welcome to you, Quentin. Thank you for being here with us today.
Thank you, Divya, and thank you for the thorough introduction.
Okay. Yeah, so I'm really looking forward to this conversation. And let's get started first by talking about your book a little bit. So the first question I have for you is, what motivated you to write LLVM Code Generation, and how does it address the existing gaps in LLVM documentation, particularly concerning backend development?
Yeah, that's a great question. So part of the answer is already in the intro that you had, which is so I've been mentoring people to ramp up on LLVM, and one of the motivation was I'm kind of a lazy guy, so I don't want to repeat myself 1,000 times. So I wanted to put into writing all the whatever it's needed to ramp up with the LLVM ecosystem. So obviously I'm kind of exaggerating because it takes a lot of work to write a book, but
Yes.
but that was the primary motivation. Give some resources for people to get started with LLVM. This is something that we've been discussing with a lot of people within the community, and especially for the backend development, that's a big need because that part in LLVM is not very well documented. And what happened is that people have to make a significant effort to get into that piece of LLVM. And then when you've done that effort, it's like, yeah, well, now I know. Why would I bother explaining it or writing it down? So it's kind of the thing that I saw time and time again. And at one point, I decided that, okay, let's really write those things down so that everybody can have a kind of source of truth for all those things. And yeah, that was the main motivation for the book. Just to add a little bit on the documentation, when you look at LLVM, I would say it's one of the open source project that I feel is the most documented. Like the documentation is very well made, but the key piece of LLVM is actually the LLVM intermediate representation, which from a backend development perspective, it's actually the middle end. So if you look at your source language, the front end produce the LLVM IR, and then you enter into the backend. But the backend is now split into 2 other pieces, which is the middle end, which does all the optimization on the LLVM intermediate representation, and then the backend with the machine intermediate representation and all that. And that's really the last part that's pretty much not documented at all, and that I wanted to cover in that book.
Yeah, that's brilliant. Thank you for that. And also the book appears to cater to both newcomers and seasoned LLVM developers. So how were you able to balance, foundational concepts with advanced topics like TableGen or machine IR to ensure accessibility, but without oversimplifying things?
Yeah, that's a good question. I have to admit, the trade-off wasn't easy, and frankly, I would say the jury is still out, because ultimately that's going to be the users or the readers, more precisely, that's going to tell us whether or not we did a good job. So for the book, I tend to always go very deep, but I present all the concepts that I use in the book so that the everything is self-contained. And so that means that for seasoned people, that may be too much content on that one, but for newcomer, at least they have the access to that information. And to strike a balance, the way I structure the book is each book comes with a quiz, and the idea of the quiz is to cover what has been presented throughout the chapter, so that instead of actually reading the chapter, you can start with the quiz. If you cannot answer the question, then that means that it's probably a good idea to read the chapter. If you can answer all the questions pretty easily, then maybe you can move on to the next chapter, and that means that you already know that part. But yeah, then I would say that for some concept, I wish I had gone farther. But the book is already pretty big. Like I think it's 600 page something. So I had to make cuts, and I made cuts on the things that are, I guess, more deeper in a sense, like going really into some of the guts of LLVM, but that are actually not that useful if you want to develop on top of it. Like for instance, if you look at you mentioned I'm the code owner for register location. So I can tell you inside and out how that thing works, but in practice, it's actually not that useful knowledge unless you want to modify it. But if you want to use it, better for me to explain you how do you use the API and this type of things. So I use the latter approach, like explaining how to use things and how you can find more information about that thing if you want to go deeper.
Right. Right. I think the chapter structure is really interesting to have the quiz at the beginning. It's both interactive and unique. And based on the information we have so far, I think the book is being received quite well, actually. So I think it's doing quite well based on the information we have so far. Okay.
So funny story. I have a few people that reached out to me directly in private messages, and they tell me like exactly what you just said, that the book just hit the right spot for them. So it makes me super happy because again, the motivation behind the book was to help this kind of people. So in that sense, at least for me, it's a job well done.
Yeah, and obviously you got the balance just right, so it's brilliant. Okay, so now let's move away from talking about the book to the technical part of the interview. And we just start by asking you about GlobalISel, for which you are the architect. Could you elaborate on how the framework improves upon SelectionDAG and FastISel in terms of performance, extensibility, and target customization?
Sure. So we're going very deep, very fast.
Yeah.
Yes. So just to give a little bit of context for people that may not have read the book yet or are not familiar with LLVM. So what I mentioned previously was like the front end, middle end, back end. What we call ISL stands for instruction selection is the transition within the compiler from this middle end to the really machine IR part. So essentially you go from an intermediate representation, so a way to represent your program that is somewhat target agnostic. So it uses the LLVM intermediate representation that everybody knows, and that it's the same semantic for all the targets, to an intermediate representation that is specific to your actual backend. So like for x86 has a different representation than AR64 and so on and so forth. And essentially at that stage, you really start to see the actual instruction of the final assembly showing up. So the whole concept of instruction selection is about getting to those instructions and picking up the best possible. So with that concept, I guess, covered, the main benefits from GlobalISel in terms of performance, extensibility, and target customization come from, so first of all, it's much younger than the two others. And that means that we were able to learn from the mistakes from the previous frameworks. And that means that it's from the get-go a much more modular design, meaning that when you do instruction selection, there is actually a bunch of steps that you have to go through. One of them, from an instance, is called legalization. And the legalization part is about when you write your program from the developer's perspective, you're using every concept that's available in the language like C++. But when you do the instruction selection, you have to actually map those concepts to the instructions that are supported by the actual target. So to take an example, it's not a realistic example, but for instance, maybe in your program, you're doing A times B, and maybe your target actually doesn't have any multiply instruction. So maybe that multiply, you have to break it down into a bunch of adds. Right? Like what you learn when you're in school, you just do a bunch of adds. And that part is called legalization, meaning taking something that's illegal for the target and make it legal with whatever is available. So now back to the design of GlobalISel. These different steps in SelectionDAG and FastISel happen in one go, or more precisely within this one optimization, I would say, and there's nothing else you can do, meaning that from the backend developer perspective, it's a monolith, and you run that thing, LLVM IR in, machine IR out, and there's nothing you can do except tweaking the APIs and so on and so forth. On GlobalISel side, GlobalISel is actually a set of different optimization passes. And between each optimization passes, you can insert your own target-specific optimization or generics one. So that means there's a lot more reuse that's possible thanks to that model. And also you have more flexibility. So that means two things. It means it's easier to debug, it's easier to test, and also there's more code reuse possible. So that's just from the pure engineering perspective. Now, in terms of performances, there's benefits that come in GlobalISel, which is GlobalISel uses this machine intermediate representation, which is core to the backend, whereas SelectionDAG has its own intermediate representation. So essentially, when you look at it from a pure transition of intermediate representation, in SelectionDAG, you go from LLVM IR to this SelectionDAG IR, and then you go to machine IR. So there's two hoops to get you to the final results. Whereas in GlobalISel, you go from the LLVM IR directly to machine IR. And that's just this one hoop is actually already a performance gain, because that means there's few changes, and that means from the user perspective, your compiler is faster. Like there's just the time you wait for your things to do its work, it's just shorter, so the thing is faster. So that's the first performance aspect. The second performance aspect is that SelectionDAG and FastISel. So we're going very deep in that. But when you look at your program, so those instruction selection work at the function level. So your different function in your, let's say your C++ file to I guess make things a little bit easier. So each function is processed one by one. Now, when you zoom into those frameworks, SelectionDAG and FastISel breaks down the function into blocks. So what you have in your C++ program, again, to simplify, the blocks that you have with your curly braces, it's the scope that the instruction selection can see. So one block at a time. And that means that any optimization that would require to do things across a block is just impossible in those frameworks. So in GlobalISel, we increased the scope to the full function, and now you have more context to do the right thing, in a sense. So again, very deep technical things, but I guess the takeaway is that GlobalISel is faster and give you a larger scope, meaning that you have better optimization opportunities, and more flexible, easier to debug.
Right. And what would you say should be the key considerations or challenges that developers may face when porting GlobalISel to a new target? And how can components like coloring, register bank info, legalizing for instruction selector interplay in this process?
Yeah, so The four APIs that you just described map to what I was describing with GlobalISel, that it's broken down in different stages. So the coloring, for instance, is responsible for, well, like its name entails coloring, which is how you map your, say, C++ arguments to the actual registers and stack location for your target. And register back info is different, and legalizer info is what I was describing, how you describe what is legal or illegal for your target. I would say to really go back to the challenges, and then we can go back to the APIs. There's different aspects. So you said an interesting word. So you said porting to GlobalISel. So that means there are two cases to consider. Either your backend already has an existing instruction selection implementation like SelectionDAG, and the idea is that, okay, you have to port that to GlobalISel. And now the question is, okay, how do I reuse as much code as possible that I wrote for SelectionDAG for GlobalISel? And now the challenge are more about how you would structure your code so that you can reuse as much code as possible between those two frameworks, which is not that easy given, like I said, there are two different intermediate representations. So I would say, generally speaking, that part is like there's no magic bullet. You have to do the work, and some of the things you have to re-implement. But when we created GlobalISel, we put in place a sort of compatibility layer using TableGen. We actually didn't spoke too much about TableGen, but which is LLVM domain-specific language that is used in a bunch of places, and in particular to describe how to do instruction selection. And with the same representation, so the same way developer, like compiler developer, so people like me describe the instruction selection actions, that can be used both in SelectionDAG and GlobalISel. So it eases a little bit the pain in that front, but there's still a lot of code to rewrite. Now, if you were to write GlobalISel from the get-go, so I also know like legacy instruction selector, the challenges are that I mentioned that in the book, but there's no right or wrong way to do instruction selection. It's more about making sure that when you put the pieces together, things works. And that means that there's actually a huge design space. Like, for instance, I mentioned the multiply example. When do you break down this instruction into a bunch of adds is up to you. So the common sense would be to do that during the legalization. But if you want to do it later, that works as well. If you want to do it earlier, that works as well. So it's more about like, okay, how do you feel it's the right way to do that? Is kind of up to you. So I give hints in the book on where is the right thing to do. But at the end of the day, what's important is whatever you design in GlobalISel makes sense. Like, you need to have a plan on how you're going to lower that thing to your target, and then you just implement that plan. So I would say one of the pitfall in GlobalISel is that you look at just, given the modular design, you can actually just look at one small piece, and then at the one small piece and the one small piece in the lowering process. And if you're not careful enough, then those pieces won't actually connect properly, or you may go into a rabbit hole of like supporting crazy things that actually are not even possible to get at that point. So that I would say my recommendation is always to keep things real, meaning that go back to whatever a programmer can write and see how that thing lowers, and make sure that every test that you write will work end to end, like from the LLVM IR all the way to assembly. And then you can break down those tests in different phases, but at least you know that the transitions between the phases are what you expect. Yeah, I guess we don't really need to go into deep details on the API that you mentioned. I would just say the first one, the coloring, is the easiest because it's really about implementing the specs, the specifications of the lowering of your what is called application binary interface, which, to put it in a few words, is kind of an API, but at the binary level. like how you set your arguments to call a function, and that's defined by whatever calling convention that is defined for your target.
Okay. So my next question is about TableGen, actually, which you've sort of mentioned. So it was, yeah. So I was just going to ask you, like, how does it facilitate backend development, and what should developers be careful of when working with TableGen?
Yeah, so TableGen is kind of hated child in LLVM. So again, TableGen is this domain-specific language, so it's really like its own programming language developed in LLVM to help LLVM development, and it's used everywhere. It's used to, for instance, in Clang, so the user-facing part of LLVM, to describe how your options are set, like optimization levels, warnings, and all that thing is described in TableGen. It's used for your target features, so meaning like when you enable, for instance, the vector extension in your program, or the part that's responsible for cryptographic extension and all that. It's used in instruction selection to define your patterns. It's used everywhere, like for your intrinsic and all that stuff. So if you work with LLVM, you'll have to touch TableGen DSL at some point. In a sense, TableGen is not that hard. It's just a language. The problem is that, so you have to learn the syntax, and it's kind of weird at the beginning. But that part is kind of easy in a sense. The thing that gets tricky is that it's just a syntax, and the actual semantic depends on what you do with it. And that part is specific to each use case. So you will see one of the things that is a little bit uncanny when you look at TableGen the first time is that for instance, you look at your option descriptions in Clang, and you look at your intrinsic. It's the same syntax, but the classes, you use concept like classes, like regular programming, and records, which is specific to TableGen, but in a sense, it's just variables. Looks the same, but what they mean in practice is completely different. And that semantic is actually not carried by TableGen, it's carried by what we call the TableGen backend that we put behind that thing, meaning the tool that's responsible for taking that language and produce something that LLVM understands. Because ultimately what TableGen is a way to automate writing a lot of code. Like when you create a new option for Clang, for instance, chances are that if you were to do it manually, you would have to register your option with the driver, connected it somewhere so that it can be used for doing the right thing, and so on and so forth. So there's a lot of boilerplate code that you would need to write, and the idea is that TableGen is just a way to describe your option, and the boilerplate is actually generated. So each backend, TableGen backend, generates different boilerplate. So it's unless you know what that backend does, it's actually impossible to know what that thing is going to translate into. So I guess the main difficulties with TableGen are twofold. The first one is that each backend does its own thing with it. So different use cases mean different code generated with it. So depending on what you're after, that means that you kind of have to do a mental shift when you work with one specific backend and with another. So same syntax, but actually different kind of programming paradigms. And the second thing is that when TableGen doesn't work, meaning that like you're not using the syntax properly, you have random error messages that are not consistent across the backends. And understanding those error messages is actually not that easy. So I touch on that a little bit in the book to help the reader on how to dig into the TableGen backend to kind of walk your way back to doing the right thing. But at the end of the day, it's kind of trial and error type of thing, which is one of the reasons that people let's put it this way. I haven't spoke to anyone in the LLVM community that actually like TableGen. So if you don't like it, that's expected. But it's a great tool. Again, it exists to help the productivities of compiler developers, but it's kind of, you have to get used to it for sure.
Okay. Right. That's brilliant. And since your book covers it, I'm sure a lot of readers will be looking forward to reading that section to deal with the sort of temperamental too.
Yes, absolutely.
So now let's talk about the latest version of LLVM, which is LLVM 20, which introduced several backend improvements, including GlobalISel refinements and expanded RISC-V support. According to you, what were some of the most significant recent backend changes, and how do they reflect broader trends in compiler infrastructure?
Yeah, so I would say the LLVM 20 release is interesting because it's there's a lot of things that you won't see as a user that are, well, you will see some, the experience of the compiler is supposed to become smoother. And by that, I mean that we spent a lot of time making sure the compiler is actually faster. So by using techniques like profile guiding optimization, which is just a way to optimize the compiler in a way that matches how it's actually used. I guess I won't go into details there, but that's kind of the idea. So the compiler should be faster compared to the previous version. And also the release management changed between 19 and 20, meaning that the way we accept patches after cutting the release branch is much more thorough. So in that sense, we're hoping to create fewer last minute bugs, and meaning that hopefully from the user standpoint, the release is going to be more stable. And then there's other changes that, again, are not something that the user will see, but that make the life of the compiler writer easier in a way. So things like when you look at your intermediate representation, there's things that are called attributes that are attached to like the functions and things like that, which are just a way to convey some additional information or constraints to the backend. And some of those attributes became more precise, meaning that we can now do more optimizations on some of those functions or have a better control of what's allowed or not allowed. So I guess to step back a little bit, you have to remember that the LLVM IR is not specific to C++. Like it's used as a backend for like Rust, for Vulkans, like GPUs and all that. So the LLVM IR must be able to represent all these different semantics from different languages. And the IR itself carry a lot of semantics, but there's also additional attributes that kind of refine what's allowed and what's not allowed. And that thing became a little bit more precise. So we have more flexibility on the type of optimization that we can do and cannot do. On RISC-V specifically, I would say RISC-V is an interesting beast because it's always evolving and everyone is coming up with a bunch of new extensions. And as the project moves forward, those extensions are being added to the LLVM backend. So that means that now what we were talking about previously, the instruction selection knows about this newer extension. So now we can use those more efficient instructions for when the extensions are available. So that means better code for the program, and then hopefully better performance for the use case that you want to run.
So now let's talk about some tools like IR fuzzer, which have been instrumental in uncovering backend bugs. How do such specialized fuzzing tools integrate into LLVM development workflow, and what benefits have you seen them to bring to backend stability?
The fuzzing tools in general, so I have some experience with them, but I've never used them in my workflow. Well, okay, let me take that back. I actually did, but it's the way I usually use fuzzing tools mostly as a hardening tool, meaning that before you get to that point, there's so many things that you need to do right in your compiler then that fuzzing is very like lasts in your to-do list in that sense. And to some extent, I feel that the fuzzing tool are really about making sure your compiler is going to be resilient on things that are not even valid in a sense. What I mean by that is that it's really important to actually run those tools on LLVM. I wish we had more time to do that type of things. But the reality is that when you're developing, or at least in my capacity, when I was developing LLVM, it was for specific products. And what's important is that the compiler works for what the user writes. So the fuzzers, in that sense, could catch some of the patterns that can be written by a user, but more often than not, they actually write things that are kind of gibberish that shouldn't, like, the IR is valid, but it's not something that real human would write. So it stresses your whole infrastructure in a way that you didn't anticipate it. And that may uncover bugs, crashes and all that stuff, which is bad for the compiler. But it's especially bad from a security aspect of it. And where I'm going here is that in particular, when we used LLVM as a backend for GPUs, the compiler actually runs on your device, like your phone, your watch, your iPad, whatever. And that means that if you manage to, like, from a security aspect, if you manage to crash the compiler, that means that potentially you're creating a path for an attacker to get into your program. It's not that easy, but every crash is kind of an opportunity, or any bugs is an opportunity for an attacker to inject some code one way or another. So in that sense, the fuzzers are very useful. But again, it's more about hardening the surface of what you can do, more than actually helping the I guess the outcome of the backend itself. Like it improves the stability, like you said, of the backend itself. Like fewer crashes and fewer weird behavior, I guess. But it's not gonna help with making the code better, in a sense that it's not that we're missing an optimization or something like that. It's just like, we need to make sure that we're not crashing on this type of things. So what I saw in practice is that those tools are very useful, but usually used by academics, and they fight bug against the LLVM infrastructure, and we go see them. So it's more about finding ill-formed inputs that are still valid from the specification point of view. And let's see if the compiler crash on those or not.
Right.
And I would say historically, it's not something that has been well covered. So it uncovers a lot of bugs, and we need to fix those, but it's definitely not the primary focus for most of the backend developers.
Right. Got it. Now let's shift to talking a little bit about ML techniques, starting with MLGO, which I believe was introduced in a paper by Truffin et al. In 2021. So with the advent of MLGO, machine learning is being applied to compiler optimizations. How do you see ML techniques influencing backend development, particularly in areas like instruction selection and register allocation?
Yeah, so that's I would say that that's something that I'm curious to see how it's going to develop, because compilers are full of heuristics, and ML techniques are actually great tools to come up with heuristics that we never thought of, and in a automatic way, which is kind of the appeal of the whole machine learning. So there's a lot of potential here. I would say the thing that's going to be interesting and is one of the challenges, how do you capture the right parameters for your heuristic to be sound, or for your machine learning model to be sound? And I guess, to make an analogy, it's kind of like, could you come up with the right pricing for selling a house by just counting the windows? There's probably some correlation, but it's probably not enough. And where I'm going is that when you look at register allocation, for instance, and what the MLGo was doing, they capture some of the parameters, but those parameters may not actually carry enough information for the machine learning model to actually do something meaningful. And I would say it's a pro in general to machine learning. Like capturing the right parameters is kind of a black art at this point. You just have to try it and do it again and again. So that's I think the first challenge for that type of thing. So it applies for register allocation, it applies for instruction selection, because again, there's this notion of what is the right thing to capture to use the right instruction or to allocate the program in the right way. So that's the first challenge. And the second challenge, I would say, is how do you influence those algorithms? Meaning that if you look at GlobalISel or SelectionDAG or the register allocator, the way the APIs are made, you may not have so much ways to actually interact with the inner algorithm that decide what to use or what not to use. So that at that point, that means that how can you inject this kind of machine learning knowledge into those algorithms may not be that easy. And if you constrain yourself to only those API, you may not actually have enough, again, information to do the right thing. So that push you into an interesting problem. Or now, does that mean that you have to write your own instruction selector or your own register allocator to actually leverage the power of machine learning? And the answer may be yes. I actually believe it's yes, but we'll see the future and we'll see how that goes. It's still not the end of the story, because depending how complex is your machine learning model, that thing takes time to run, and that time is actually reflected in your compile time, so the end user. And is your user ready to wait, I don't know, 10 seconds for maybe a 1% improvement in the final optimized code? Maybe. Are they ready to wait 10 minutes? Maybe less. Are they ready to wait longer than that? So there's a trade-off here that's interesting, and that isn't new to compiler, because there's a lot of problems in compiler that are actually well understood and that can be solved optimally using like integer linear programming method, for instance, which are based on solver and all those kind of things. And we just don't do it because it's just too slow. So it's like if something takes 1 hour for you to get a few percent improvements, that's the point. What's the point? So there's a lot of trade-offs and things to do there, but I would say it's very promising. There's a lot of interesting research to be done there, and we'll see where things go.
Yeah, it should be interesting to see what happens a couple of years down the line, isn't it?
Absolutely, yes.
Now, can we talk a little bit about MLIR, which introduces a multi-level intermediate representation, offering more flexibility in compiler design? How does MLIR interact with LLVM's backend, and what advantages does it bring to code generation for heterogeneous systems?
Yeah. So LLVM IR is kind of a new addition to the LLVM family. And like you said, it's a multi-level intermediate representation. And actually what sits behind this multi-level word is that it's a framework for you to define your own intermediate representation. So you can really, you have a huge space of design space for new intermediate representation that you can use. And in particular, it's very nice to model things that may happen across boundaries. So what you just mentioned with heterogeneous system, within the same IR, you can model both your modules or your whole, let's say, file, C++ file in a way, for both your GPU and your CPU. So that means that now you're opening up yourself to optimization that are across different backends, which is not possible at all on LLVM. Like for instance, let's say your hosts, like your CPU calls a GPU to do something on the GPU. Now you see both sides of the equation, and that means that maybe some of the work that happened on the CPU, you can actually push on the CPU with some optimization, or the other way around, or you have a cost model to move things in different ways and things like that. So it opens up a lot more optimizations, but it's not free. And what I mean by that is that anything that you do at the LLVM level is in a way disconnected to LLVM. So the way you can think of it is LLVM IR actually sits on top of LLVM, sorry, MLIR sits on top of LLVM IR. So again, if you have this front end that was producing LLVM IR, now you can look at different languages like framework like PyTorch, which is used in machine learning, for instance, that can produce MLIR, and that LLVM MLIR is then lowered to LLVM IR. So it's essentially one additional layer where you can do things. And usually in machine learning, it's where you do your what they call graph optimization and stuff like that. But all these optimization use their own implementation. They're not reusing LLVM. So LLVM is still used. The backend is still used, but only to produce the I would say really the pure backend things when you already decided where things will run between the CPU and the GPU, for instance. So I would say the beauty of MLIR is that you actually can do whatever you want. If you want, you can actually directly generate assembly and things like that. But anything that you do, you would have to re-implement. If you're not using the LLVM backend, that means that you have to do it yourself. So there's, I think, an interesting opportunity or challenge to make sure that we reuse some part of the algorithm from LLVM IR within MLIR, or essentially make things more homogeneous in that sense. And we'll see where that goes.
Okay, brilliant. So my next question actually, I think, loops back a little bit to debugging, which you sort of talked about when we were talking about IR fuzzer and things like that. I mean, we know debugging backend passes can be complex. So are there any tools and methodologies you personally recommend for effectively diagnosing and resolving issues in code generation?
Yeah. So I actually cover that in the book. It's really a key problem that you face when you use a compiler. It's a very complex system. So yeah, having ways to help yourself for this type of debugging activity is indeed very important. So the first tool that you can leverage is that LLVM comes with a lot of logging mechanism where you can actually see what happens while lowering your program through the LLVM pipeline. So you can enable that. Then there's when you start to see which optimization is acting weird, you can enable additional logging mechanism for this one optimization alone. But that's more like, okay, you kind of already know what you're looking for. Now, to step back a little bit, one of the tools that are super useful in LLVM is tools that are used to reduce the size of your input. Like if you think about your IR, usually it's, to simplify, it's kind of, you get the whole C++ file or whatever input language you're using, and that thing can be huge. And LLVM provide tools like LLVM extract or LLVM reduce that allows to just take one function from that file and just compile that thing again and again. And LLVM reduce goes one step further, so it needs some input from the developers, but with you can guide that tool to say, okay, for instance, if your compiler crash, it's kind of the easy things to relate to. You can say, okay, as long as my IR crashes in a way, like for instance, it asserts in whatever register location, let's say, you can say, okay, as long as my program asserts at this particular point, just reduce the size of the IR, and that tool automatically will remove things so that at the end of the day, you end up with the minimal reproducer. And that means that after the tool runs, instead of debugging like thousands of lines of intermediate representation, you may just debug like 10 lines, and things gets much more tractable at this point. So, but that's kind of my first advice. It may not be always possible, in particular that what I just described works very well when you're tracking a crash in the compiler, for instance. But I would say the thing that kind of the nemesis of the compiler engineer is when you're tracking miscompile, and miscompile are like, from the compiler standpoint, everything goes great, but when you run your program, it doesn't do what you're supposed to. So now it's like, okay, where do I even start? And there's actually techniques here that you can use as well. So first of all, let's assume that you can disable what is called inter-procedural optimization, because that kind of messed up everything. Meaning that, so inter-procedural and optimization do optimization across functions. That means that now you're actually across files as well, depending on how you do it. So that means that now your files are not your hermetic unit that you can debug alone, that you have the whole program. So that's kind of problematic. So first of all, try to disable that and see if the problem still arises. And if it still arises, that's great news. That means that now you can leverage what I would say the ABI boundaries. So meaning that when you call a function, if you're compiling it correctly or incorrectly, it's the boundary is still the same, assuming you haven't messed up that part of the implementation. But what I'm saying is that in your program, if you're calling a function foo, it doesn't matter if the function foo has been, for instance, compiled with GCC or with LLVM, it's still the function foo. From a pure API standpoint, it's the same function. You don't care on the actual implementation, and it's the same thing with the ABI, just one level below. So that means that leveraging that particular property means that now you can start to look at all your functions, compile it with, for instance, optimization and without optimization. And then you can just, with just changing the way the linker works, you can actually track down which functions or which file contain the problematic function, and then split your files and then look for the function. And to a point where you can then, I'm going into a rabbit hole, but essentially you can create a smaller function automatically on that stuff. And there's a few tools within LLVM that you can leverage to do that. But in the end, you can end up with automatically a really small function that you need to debug. And at that point, the ultimate thing is that you have to stare at the code and look at, okay, why is my assembly not doing what it's supposed to do? And at least so far, there's no tools that can help you with that, but maybe machine learning will be there somewhere. You can train your machine learning to say, okay, what is the semantic of this specific assembly sequence, and check if it matches and stuff like that. But we're not there yet. For now, the last line of defense is you staring at assembly code.
Okay. Okay, thank you for that. It was really insightful. Now let's sort of zoom out a little bit. And I want to ask you, for developers interested in contributing perhaps to LLVM's backend, what areas do you feel currently need attention, and how can new contributors effectively get involved?
Yeah, so that's a great question, and a question that comes a lot for newcomers. My first comment would be step back a little bit and think about what contribution means. Because for a lot of people, contribution means writing code and sending patches. That's actually not the only way to contribute to an open source project. And in particular, one thing that helps a lot is filing issues. So like if you're running an IR further, for instance, it's great to know that the compiler crashes in specific conditions. So filing issues is a way to contribute. And also, like, if you look at LLVM, I'm not proud of that, but if you look at the bug tracker in LLVM, there's actually a gazillion of bugs. And if you look at the curve, it's actually increasing faster than we have time to fix them. So one way to help the project and contribute to the project is actually also helping on triaging bugs. And it's a very good way to get used to the tools I just mentioned for reducing IR and things like that, because now you can take an actual user bug and see what it takes to reduce it so that it's easier to debug. And if you don't feel comfortable debugging it yourself, just the fact that you're helping with the process of reproducing the issue helps the person that's gonna actually fix the bug down the line. So anything helps. Like, any time you can spend on the project is going to help someone else in the project. So that's on the issue side. Now there are also need helps on the reviewing part. So like patches are one of the way to contribute to an open source project. But when you think about it, if nobody is reviewing those patches, then the project is not going to move forward. So it's very important to also help on the reviews, and it's also a good way to get started because you can pick like an area that you want to learn, and you can see how the code is being changed by the different contributors, and little by little build some knowledge of the related code base, and you can start like very simple, like, okay, you wrote that, but I don't understand that. Like, could you put more comments or something like that? So maybe the thing that is missing comment is something that's obvious for the contributor, but the fact that it's not obvious to you, it actually could be an indication that it's not obvious for someone else. So it's always good feedback to have. And then ultimately, when you want to contribute patches, like I said, there's a gazillion of issues. So there's a lot that you can fish there and start to contribute on that front. And if you are willing to step in and help on that stuff, feel free then to connect to contributors that will help you write the patch, pushing it for review and all that stuff. And I would say, finally, there's a lot of, historically, LLVM is not that good on loop optimizations. So there's a lot of things that could be improved on that front. So if you're willing to kind of do a real, not real, but like deep compiler algorithm and whatnot, that's another area that needs help. And generally speaking, like, new research comes out of academia every month on compilers, and if you think that something could be interesting to LLVM, you can try to implement it in LLVM and try to contribute it to the project. So there's no shortage of contributions, let's put it this way.
Yeah, there's a lot of opportunity. That's brilliant. And that brings us to the last question for this interview. So, Quentin, looking ahead, what trends or technologies do you anticipate will shape the future of LLVM backend development, and how should developers prepare for these changes?
So we already talked about it a little bit, but I think MLIR is one of the key pieces that is being adopted pretty much everywhere. Well, okay, let me step back a little bit. When I say everywhere, is that I see it a lot being used in everything. So if you look at, for instance, the language Triton that's used to write performant ML kernels, it's based on MLIR. If you look at what NVIDIA is doing with their Qtile, and so like different kernel authoring type of tools, for which is the kind of the nerve of the war for ML related application, which is the hot things nowadays. There's some MLIR somewhere in those stacks, and that means that knowing MLIR is kind of something that you must do when you want to go into compiler development. So it's not really backend at that point, but like I was mentioning previously, there's some direction that the MLIR is feeding directly to the backend. So it gets important, in my opinion, to know the full stack, so the full compiler stack, I mean, so that you know at what level you need to do which optimization, and producing the right LLVM IR from your MLIR, so that the backend can do a good job. Because the one thing that people may not realize is that LLVM is a great C++ compiler, and it does a lot of great things on other languages. But the primary IR that has been seen for decades in the backend come primarily from C++. And it's completely unconscious at this point, but a lot of optimization has been tweaked to work very well on C++, and that may not translate that well for other languages. So that means that you have two options at this point: is either you improve the backend to perform well on those kind of weirdly shaped LLVM IR in that sense, or you modify your front end to produce something that looks more like C++. So that means, again, like knowing the full stack gives you options and kind of help you understand where is the most efficient way of doing something. I would say, generally speaking, going forward, it's kind of like repeating something that I'm sure people have seen a lot, but leverage AI to move faster. AI is a great tool to like write algorithm or understand a piece of code Like you can even take an LLVM function and ask AI, okay, what does that thing do, and things like that. It's a great tool to learn and to move faster. My word of advice would be, if you produce code with AI, just make sure that you understand what it does. And in particular, the way I think about it is like, if tomorrow you don't have access to AI, can you still understand or write that type of code? And to me, it's important. And I'm gonna speak from experience, is that some companies or some projects forbid you to use AI because of some copyright and all that, and secrets and things like that. So AI is great, but you need to be able to do your work without AI as well. So use it where it makes sense, and leverage it to move faster while still being in control. I guess that's the takeaway.
Yeah.
And I guess just to close the thing, if you look again at the full compiler stack, what's in the end, if you want to really leverage the compiler, the best thing that you can do is make it more accessible to the end users. Like, one of the reasons that Triton is so useful, so this ML kernel authoring language, it's because it kind of removes some of the barrier to have access to lower level concepts from a programming language perspective, but allows the developer to do the right optimization for their program. And sometimes the best way to help the developers is not to make the compiler smarter, but it's to give more knobs to the user to use the compiler the way they want. And yeah, I think that's my closing remark. Like, the compiler is not the ultimate tool, is just a tool that it's our responsibility to make it more useful for the developers.
Yeah. Brilliant. And that brings us to the end of this interview. Quentin, thank you so much for joining us and sharing your experience and deep insights with us. It's been a real pleasure talking to you.
Thank you, Olivia. It was a pleasure to talk with you as well.
And to our viewers, thanks for watching. If you'd like to dive deeper into the topics we've discussed, check out Quentin's book, LLVM Code Generation. It's a hands-on guide to building and extending LLVM backends, backed with real-world examples and expert insight into compiler internals. You'll find the link in the description below. Until next time, this is Divya for Deep Engineering.